Okay, I believe the recording has started, so I can start my talk. First of all, thank you everyone for stopping by. I'm Marko, and today I will talk to you about a simplification, in a sense, within the transformer architecture, as well as extensions where the simplification can actually be a bit more complicated to extract more value out of it. This is still work in progress. So the models that you will see trained are relatively small scale. There's a lot more things to do. So any feedback, any questions is more than welcome and will surely be of great value. So yeah, if you have any questions, by the way, feel free to as was mentioned, write them down in the chat as soon as you get them. Yeah, without further ado, I'll start the presentation. So this is how the presentation will go. First of all, I will present you with the results, with the empirical results, so that you can get a little bit of a feel of what these results bring. Then I'll talk maybe a bit about the outlook, what can be done next, and then I'll pull us back to the theory part, so that we don't bore ourselves with the theory right away. And finally, I might, should the time permit it, talk about the challenges that we're facing and the future work. Something that we're relatively proud of in this work is that most of it has been theory first. So we came up with the theory first, and then we started experimenting. So yeah, the theoretical prediction that we're making is that basically WQ matrix, or the weights for the queries, can be replaced with the identity matrix. So this basically means that your queries will be your original data points, whereas your keys and your values in the attention, they will be linear maps of your input. I mean, this is also a linear map because it's the identity, but it's the simplest one. A little bit of a refresher about the transformer. So how it works is you have your input data, in which you have in each basically row, you have the embedding of a token. And after the embedding is said and done, you norm and scale usually the input. Then you get these projections, these linear maps. The weights with the weights of the queries, you get the queries. With the weights of the keys, you get the keys, and with the weights of the values, you get the values. Everything goes inside of the attention, and then that gets again multiplied by the WO matrix, and then you have the feed-forward network afterwards that comes just afterward. And of course, as you know, in the standard transformer decoder-only architecture, this gets iterated, and then you get your language modeling head, or the token classification head at the end. A small reminder that here the I represents the number of the layer, and when we talk about heads, we will use a single matrix, which will be basically a concatenation of all the matrices per head. And then when you multiply X by, for example, WQ, you get the per head projections. So this might be something useful to refresh upon. Yeah. The experimental setup is pretty basic. We take Nano GPT, which is a small scale GPT-2 or GPT-3 architecture. As we know, not a lot has changed in the attention part. Of course, there have been improvements, but the core of it is basically well, more or less the same. One thing just about the chinchilla optimality, the chinchilla is about at what compute do you get the best model, and this is undertrained if you train at 1 times chinchilla optimal. In a sense for the model, and here we kind of overtrain our model just to see if these things that are learned are how to say hard gains rather than the easy gains. So up until chinchilla optimality, you get like the easy gains for the model, and then the model gets the more difficult ones to make. Yeah, in the baseline, you have a model with 124 million parameters as the baseline, and then we also reduce the number of parameters artificially, just to get like a smaller model, just to see how much the log loss will drop. And then we call our model where WQ is set to the identity matrix to be the reduced model. We take one which has just this reduction, and then in another model we take WQ to equal the identity, and the number of parameters that is saved here is transferred to the MLP. So the MLP gets a bit wider. This MLP here, these things here get a bit wider, just to see whether it might be optimal. It might be better to put these parameters into that part. So yeah, when we were doing this, there were some theory predicted adjustments that we needed to make. First of all, the attention scaling. Well, when you have the identity, you do not have a linear map multiplying your input x, and with some calculation, you get around 1.8 here instead of the 2. But we said, okay, we will play it safe and put the 2 here. Another thing that happens is that you lose this bilinearity well, not in X through the weights of the queries and the weights of the keys, and so your optimization becomes a bit easier because now you only need to optimize to one weight matrix here. So this is something to keep in mind when we're doing the optimization, and this actually allows for higher learning rates when we were training this model. And not only does it allow them, but it also functions in a sense something similarly to the query key norm, where we actually normalize the queries and keys, with the difference that we do not apply any strict normalization to the queries or the keys. In a sense, the queries are already pre-normed because of this, so this becomes identity here. All try to optimize in a sense together with the table. You can see that when you put to the WQ to equal the identity and you enlarge the MLP a bit, you get the best model. You get the best validation loss, and the training curves are pretty interesting because you see when you put WQ equals to identity at the start of the training, the loss is much worse, and then at the end of the training, it catches up. And you might think that you need the longer training runs just because of this, but this is not only because of the length of the training run, but we also have a scheduler. Basically, we're reducing the learning rate as time goes by. So it's mostly about the reduction of the learning rate that this is impacted by. So yeah, and the baseline, it's in the middle, and if you artificially reduce the number of parameters through the MLP or through the dimensionality of the model, you get the worst validation loss here. They overlap. This is why it looks like the same line, because basically these two they have the same validation loss. And you will see, as you can see, the WQ equals identity. The simplification that was kind of predicted basically matches the loss of the baseline. Of course, we have checkpoints, and this is not too difficult to train. It takes around 2 days on a 5090 to run. On a slower GPU, it might take like 3-4 days, 5 days at worst on a single one. If you have a better GPU, more optimization, you should be able to do this very, very quickly, because this is still a small model. And yeah, here we count the non-embedding parameters. So the key result here is that the WQ equals identity works at this scale. And one thing to have in mind is that the smaller the model, the more the parameter reduction usually impacts it. So we would expect, because of this, that this should work in higher dimensionality. What this brings is that you reduce the number of attention parameters by 25% because you remove one of these matrices. All of these are D by D matrices. Keep in mind these are stacked weights per head. So when you stack all the weights together, you get D model by D model matrices. Parameter reallocation actually improves the performance. And if you allocate the same parameters, the MLP, instead of having width of the hidden layer 4, you put it 4.5, and then in this family it performs the best. One thing here is that these are single runs, but when you train far beyond chinchilla optimality, these these results are pretty robust. So because these models, after 100 million parameters, they are relatively large, and yeah, if you run them on different seeds, you should be getting pretty much the same results. Of course, these are only in the repo, so one can easily change the seed and yeah, try it themselves. One thing that we noticed here is that, as I mentioned earlier, this setup tolerates much larger learning rates. And not only does it tolerate much larger learning rates, it also does benefit from having a higher max learning rate and a lower, what's it called, the minimum learning rate than the original model. So this was a bit bizarre. And one thing that we should do here actually is to investigate the gradients. So is there maybe part of the model where the gradients are really large, and this is happening, versus some other phenomena that maybe this type of architecture allows for? Because keep in mind, if you reduce this to the identity matrix, you get like a skip connection within the attention. So you get like another skip connection here. So that might also be impacting things. So yeah, instead of the standard, you go from the maximum learning rate to the maximum divided by 10 as the minimum learning rate. Here we have a larger range where we go from the maximum to 1 over 100 of the maximum learning rate. This was empirically shown to give the best results. And why the stability? Again, as I said, it's because of this. Our guess is that we have this linearity in this parameter instead of the bilinearity in these two parameters or in the optimization. So this is our initial guess. So an intermediate conclusion from this small scale experiment would be that the WQ does not contribute much more. A learned WQ does not contribute much more to the identity. And any linear projection is kind of redundant. So the natural question is, can we do better? And before I move forward, I would just like to mention that what I presented earlier, at least in theory, was first explored by Niels Graef around 2 years ago, which we were unaware of until 1 month before we first put our work online, and who has helped us a lot, by the way. So yeah, just something to mention. And the part, can we do better, is going one step further, asking, okay, if we have these wasted parameters, we tried moving them to the MLP. It was beneficial, but can we do better? And if you want to do better with these parameters used for the query itself, you have to add non-linearity, because any linearity, in a sense, can be absorbed, as you will see in the theory, more or less under mild conditions. So the next experiment that you will observe here is that the queries become, instead of a linear map, you take x plus an MLP of x. So this basically adds non-linearity to the query, but also keeps this linearity here kind of grounded in a sense. We take a bottleneck MLP here for a very simple reason, that we want to replace exactly d squared parameters, because this is the weight that WQ has. So we don't want to be adding any more parameters. Of course, we add some normalization on top of F theta because we didn't have a lot of computation available. So we're like, okay, let's make it as stable as possible for our training. But yeah, the number of parameters doesn't change. Then you just add something linear to this. This is, of course, to the power of 2, and you add some parameters that don't really impact anything. So the scaling here doesn't impact anything much. So in that sense, the next question is, how will this nonlinearity perform? And there has been work done on the nonlinearity, but very little, so to speak. And we believe that the reason for this is that, first of all, nonlinearity can bring a lot of instability, because in the attention you have this bilinearity and so on, and this can be very problematic. And on top of that, I don't think that it was tried for one to put like a skip connection here. On top of that, we're matching the exact number of parameters. So this is a very controlled setting. And we're only attacking the query. One might ask, okay, why not the keys? Well, if you put x plus something inside of the keys, then you're centering around self-attention, in the sense that every token will try to attend itself a lot. So this is why we attack the query only. And of course, we have limited computation. So, and this is theoretically reasonable to do. So we attack the query. The good thing about this is that this doesn't touch the attention itself. The calculation of the attention stays untouched, in the sense that you calculate the queries times keys transpose in the ordinary manner. Flash attention, the difficult part, is untouched. So yeah, you're not adding any overhead, any significant overhead. And then, of course, as I mentioned, why we keep the skip connection? Well, first of all, it's a good prior. We know that if F theta is equal to 0, and it can be learned, that can happen, then this becomes exactly the original the original WQ equals identity. So we have a good prior there. We have the gradient flow because of the identity, and also we keep full rank expressivity. As I mentioned, this F theta is an MLP, a bottleneck MLP, which compresses the data in d/2 dimensional space, and that's data compression, nonlinear or not, it is compressing. Whereas this X here can basically keep the full dimensionality of the data. So this is another reason why this skip connection here is actually a good idea, at least theoretically, in our opinion. And the results here are surprisingly good. Why do I say surprisingly? Because if you were to allocate the parameters just to the MLP, as is done here, you get around 0.5% of logloss improvement, right? 0.5. Here you get 2.4. So from 0.5 to 2.4, that's a huge improvement. And it's at 0 extra parameters, although almost 0 extra parameters, less than 0.1% of parameter change, because of these scaling parameters, which are pretty small. And we also tested this with a much wider MLP with the original model, where we add an additional 12.5% of non-embedding parameters to the original model, so to the baseline, and this only brings 0.94% of logloss improvement, which is, again, pretty far from 2.4%. This, if you try to extrapolate using the scaling laws, this should be, as if you added 30% or more parameters to the model, which is again, as I said, pretty surprising. But yeah, we will get back to this as something that we're also working on, which is explaining why this actually works so well. One part is that we believe that this projection from the d-dimensional space to the 3D dimensional space of queries, keys, and values, and well, the skip connection if you count it for the 4D dimensional space, is actually pretty constrained. And when you add nonlinearity, you allow the space to be more filled, so to speak. So this is one hypothesis of why this works well. Another hypothesis is that, well, you allow for nonlinear interaction, so to speak, within the concepts of the, of what they call them in the mechanistic interpretability crowd. Again, these are just hypotheses. We're not experts in these fields. It's yeah, something that we were considering as, again, why this works this well. But back to reality. This again is just small scale. It's trained on language completion. This works for any self-attention mechanism. So it means that we can work for decoder only, encoder only, and then mixed masking, if you will. But you have to have a single self-attention model. So self-attention and the mask, any mask does the trick. But I'm not sure how this would work if you have a decoder and an encoder part, for example. We haven't done the calculations there. So there are a lot of things to cover here. There are other modalities to cover. There are other tasks to cover other than language completion. And for example, here we have not tested downstream tasks for a very simple reason that in small models, the downstream tasks correlate very, very well with the log loss. So you need to go like after a certain model size where the log loss is not very indicative of the downstream task performance. And there are other architectural adjustments to try and other hyperparameters to try. So this is, as I said, just a just work in progress. So this is not finished work. There's still many things to do. Now I will go back a bit, take a step back, and talk about the theory part of how we got here. So if you have any questions about anything prior, maybe I would suggest this is the good time to write it down so that you do not forget it afterwards. Yeah, because what I will say next is trivial. So yeah, you can use these seconds to write your questions should you have. So yeah, the initial assumption that this started with is something that's trivially wrong if one understands the multi-head attention. So if one looks the single head attention, the queries times the keys, you get this nice matrix product where your input is multiplied by WQ to get the queries, and your input is multiplied by WK to get the keys. And then if you do a little bit of algebra, you get this nice part here where you can actually merge these two parts in a very single in a single matrix very easily. You don't need to be training anything. You don't need to do any of this fancy stuff. And in the single head mechanism, as I said, this is trivially true. In the multi-head regime, however, this is wrong. I mean, it is true if you look at it head by head, but then you get a large matrices here. And the idea of the heads is to compress information. So if you look at the per head weights of the keys, queries, or values, you will notice that they go from the dimensionality of the model, and their output dimension is the dimensionality of the model divided by the number of heads. So they are how should I put it? They're downstream projections in a sense. They reduce the dimensionality. And if you were to do this merge, you'll get a large matrix which defeats the whole purpose of the multi-head attention. So for that reason, this in the multi-head setting, this is completely wrong. You do obtain some degrees of freedom here, of course, but they're not a lot. So it's the number of heads times the dimensionality of each head squared. Again, not a lot of degrees of freedom, as one would expect, is gained here. The starting point here is Well, the multi-head attention. The multi-head attention is the concatenation of the per weights of the heads. And if you do some algebra, you will notice that there exists a function g such that the multi-head attention of the input x and the values is some function g of the projections of the queries, the projections of the keys, and the projections of the values, which means that the multi-head attention is actually invariant under this map here. So if you multiply the input by the same theta, and then you do this multiplication here, the multi-head attention will not change in value at all. So just stay here for another 5 seconds because there's a lot of equations, but yeah, this is a symmetry that we will try to exploit. Again, keep in mind that we're not hiding the heads. The heads are within this single matrix where we concatenate them together. And of course, we have here WO at the end, and well, actually, the WO is missing here, and you'll need a WO here. But the WO is not impacted here in these calculations, so it's it's not a B. So what we can do is say, okay, can we set this theta, because it could be an invertible matrix, to be equal to WQ? And first of all, why should WQ be invertible? Well, almost every matrix in the Lebesgue sense is invertible. So this is like a reasonable assumption. So of course, it can have you can have problems with very small eigenvalues, but it's still a reasonable assumption to make in our opinion. And then we can define the reduced weights in this case. And then the multi-head attention, okay, it has WO, becomes the multi-head of this reparametrized X, and then these reparametrized weights here. So the only thing we need to do in a sense is pre-compute this XWQ, meaning that the input should already have the WQ pre-computed within the data that arrives there. So the question is, can we do this? And as I said, under mild assumption, we can do this by having each layer of the transformer pre-compute WQ and pass it to the next layer. So this means that the first layer will pre-compute WQ and will pass that information to the second layer, and so on down the line. So you have first the embedding layer, and of course, you can multiply your embedding layer by this WQ1, which means the WQ for the first layer, and then the first layer gets this pre-computed, so it kind of gets it for free. And then you carry this on up until the next layer. And again, this is in the simplified setting where you do not have the skip connections, because otherwise you should be having skip connections here, and these kind of ruin the math. However, these bring us to another interesting result and another empirical result, because we did test whether this change can be done under some generic matrices, and it turns out that yes, you can very nicely approximate this change even when there is skip connections present. But you can approximate it, not get something exact. And this is a problem in the sense that you cannot do this explicitly on a pre-trained model. So you cannot take a pre-trained model, just do these computations, and then have your pre-trained model without one of the weights. That is not possible because of the skip connections. And another obstruction is the normalization, the pre-norm that's preceding every layer. Well, every attention layer and every what's it called? And every feed-forward layer. So what we covered theoretically is that we can do this in the multi-head attention. We can do it when we have skip connections around the attention. But the problem that we have to prove this theoretically is when you have skip connection around the MLP. So in that case, you can only do it in certain cases where, for example, you have something like the Albert model where you stack the same weights and you iterate the same layer multiple times. In that case, you can do it, but in the general transformer, you cannot do it. So that's the weight shared transformer. And in the layer norm, the layer norm part, the question is, can this map even pass through somehow this linearity, this change of variables, can it pass through the normalization? And our theory says that it can be done. So the layer norm can transform. You can have this semi-conjugacy where this linear transformation gets worked out, and you can still have something close to that linear map at the end. But along the way, I mentioned that we have problems when we have a skip connection around the MLP, at least theoretically. And we actually came up with, I have to give credit here to Anthony because he was the main driver behind this, to the skip connection and the MLP itself. So the question here is, can an MLP absorb its own skip connection? Right? So if you have just an MLP on one hand and the same size MLP on another hand plus a skip connection, the question is, if one of these is fixed, so let's say you have a fixed MLP, it means you have a fixed weight, single hidden layer MLP. Can you fit another MLP such that the MLP plus a skip connection is exactly equal to this one? And the answer for the most utilized activation functions is actually no. So these two are disjoint function classes, generically disjoint function classes. So almost surely you cannot have these to overlap completely, and almost surely they will, how should I say it, be not exactly equal to each other as function classes. So yeah, the why this is important? Well, for example, in the hyperconnections case, we saw that empirically, labs like DeepSeek use the manifold constraint hyperconnections, and they do get better results than in the part of the skip connection. And so the question, asks itself: can these two actually represent the same thing? Is it an optimization problem, or is it a representability problem? What this theory says is that there might be a representability problem as well, right? Because you can easily pass from this problem to a problem like, for example, a skip connection and a learned connection, right? Because up until now, to my knowledge, most theory that has focused on skip connections has focused on it as an optimization tool, as a gradient propagator. But not a lot of work has been done, to my knowledge, on how it affects the representability itself. So this is something, at least in my opinion, it opens interesting questions. There's also work by G and his collaborators where they actually train transformers without a skip connection, and they do sometimes even get better results. So this also, again, goes in that directions, but incorrectly. Of course, as I said, we cover a lot of theory. At the end, you still need to do the experiments. The theory is nice. You need the experiments. There's a lot of hyperparameter sweeps to be done. There's scale to be covered. So yeah, there are challenges here and opportunities as well, not challenges only. The unexpected gain itself is also an opportunity because it presents itself as something to be explored at scale and explained as well. Because it kind of underlines a mechanism where it unlocks probably representability that allows for much better log loss. And this is again in the overtrained regime where usually improvements go to die. When you overtrain your model, usually the improvement gets these architectural tweaks, they get very close to the original. Whereas this one, it persists exactly there. We have hypothesis on why it works. Well, first of all, you have the symmetry breaking, of course, and the other one is that it decouples this linearity block, where you have a linear projection from the d-dimensional space into the 3D dimensional space. Let me just point that out, which is this one here. So you have from a single X, you have projections into 3-dimensional space, which is, if you stack these together, you get a single matrix from D to 3D. And it is a linear map, so it cannot fill the entire space no matter what you do. Of course, you have concentration bounds and so on, telling you that this is maybe not that catastrophic, but the experiments here show that there's still some care to be taken. So yeah, this is about the unexplained gain, why we hypothesize that to be the case. There's the layer norm of obstruction, in which we show actually that the MLP prior to each layer will need to approximate some function, some concrete function, in order for us to be able to move the linear map through the layer norm. Because keep in mind, the layer norm has this epsilon regularization, which makes it to be, it's not a projection on the sphere, but projection onto the space itself. You have an open set. It's not a projection of the sphere itself. It's a projection into the ball. So you do have these freedoms within it that get exploited in order for us to do this. This can be, of course, looked into more in detail in the paper, or I have extra slides if anyone is interested. We have this result called the layer norm semi-conjugacy. So the summary of this part is that you can probably save some of your parameters and compute. But if you reallocate these parameters to nonlinearity at the same budget, then you do get much better results. Of course, this is, again, as I said, tested on a small scale. There's still a lot more work to do. Before ending this presentation, I would like to thank Niels Graef, Borjan Geszkowski, François Yvon, Jiping Yi, Haris Mandal, Igor Sheva, and Dimitar Pishevsky for awesome discussions around topic and suggestions and connections to people, who all of them have been very, very helpful. Of course, we're looking for collaboration to explore this further. You can reach us out at these emails. I'd like to thank everyone for your attention. And should you have any questions, please feel free to ask them now. Ask us through an email. Get in touch. Thank you very much.